Okay, so Bismillah Rahman Rahim. So today we are going to start with the seventh lecture of our course. In this lecture, we are going to discuss the inelastic behavior of multi-story buildings. In the previous lecture, we talked about the inelastic single degree of freedom system. So in case of multi-story buildings, we will see that the considering a multi-story building as a single degree of freedom system cannot predict the response accurately. So we have to adopt the methodologies for the multi-degree of freedom system in order to predict the behavior of multi-story buildings. So we already demonstrated in the past lectures the complex dynamic of multi-story building require idealize a system with the multiple degrees of freedom for analysis of their response to earthquake. So I'll just make a note here. Okay, so multi-story buildings, they are idealized as multi-degree of freedom system for the response assessment. Okay, and we know that most of buildings they are designed for the base shear smaller than the peak base shear. That is computed under the assumption that the structure is linearly elastic. So if you remember, uh, always the elastic base shear is more than the base shear for which we design our structure. So the same is also the case in a single degree of freedom system, but always also in the multi-story buildings or multi-degree of freedom systems. So we know that the earthquake response of multi-story buildings deforming into their inelastic range is of central importance, because if you design something for a base shear that is less than the elastic base shear, so obviously what will happen is that the structure will respond into the inelastic range. And if I just demonstrate this by the help of the force and displacement behavior of structure. So for example, if this is force on the y-axis and this is displacement on the x-axis. So if it is entirely elastic, this will be the behavior of a structure, force and displacement, and the peak force that it will experience during the earthquake response will be VE. But the problem is that the yield force design is even here. We do design for this, but the yield force is also less than the VE. So what happened is that the structure will go into the inelastic range. So understanding the inelastic behavior of a structure, it is of prime importance in the design as well as in the assessment. So in this lecture, we will talk about the various methodologies for the analysis of multi-degree of freedom system for elastic as well as for the inelastic multi-degree of freedom system. If you remember, in one of the lecture, we already talked about the linearly elastic multi-degree of freedom system. In the lecture, we will also talk about some of the importance of various assumptions used in the modeling and analysis of structures. For example, the preparation of numerical models, the importance of the P delta effects, and some other importance related to the definition of ground motions. So let's talk about the analysis procedure. The so the most accurate procedure that is used for the analysis of inelastic structure is the nonlinear response history analysis. Okay, in short, it is also abbreviated as RHA, response history analysis, and nonlinear for the fact that this is for the inelastic models. So if you remember the equation of the dynamic, the general equation is the m times the acceleration plus the damping times velocity plus the uh, stiffness and displacement, but I will write the Fs term, the restoring force, stiffness base, there is dependent on the displacement as well as is dependent on the sign of the velocity. And this will be equal to the minus mass. Then there is a vector that defines the direction and the ground acceleration, the input excitation. So this is the general equation. In this equation, if you see in the elastic single degree of freedom system, this was Ku. But since the stiffness of the inelastic system is not constant, it is changing, and also there is the sign importance, whether it's positive or negative. So with the history of displacement, the stiffness is changing, and so the whole force is also changing here. So we have to represent this in a generic way. Okay, and if you remember the behavior of an inelastic element, we already talked about this. For example, if this is a force and this is a displacement, so there is an elastic branch for this, there is a plastic branch, and then there is a unloading branch as well as the reloading branch. So the stiffness is, this is the initial stiffness, uh, which is K. This is the post yield stiffness, post yield stiffness. In case of the elastoplastic, the EPP, the post yield stiffness is equal to 0. Okay, because we assume that it is elastic perfectly plastic or elastoplastic. And this stiffness is also equal to K. This stiffness is also equal to K. This is in the case when the stiffness is not degrading, or the technical term is that when the stiffness is not deteriorating. So in that case, the this branch, which is this one, let me mention here, this is the loading branch. This one is the unloading branch, and this is the reloading branch. Okay, the reloading branch. So in case of the non-deteriorating structure, the three stiffnesses remain the same. Okay, but we see that in real structure it is not the case. The stiffnesses it changes because this is a very idealized system. But anyway, the idea here, just to mention that this Fs term, which depends on the displacement as well as the state of the structure. For example, it depends on where the displacement is, how much the displacement is, because force is directly proportional to the displacement. But what is the state? Which means whether you are in the loading branch, elastic, loading branch, plastic, or unloading branch, the unloading plastic, or the reloading branch. So depending on where you are and what is the state of the structure, this force will change. In case of a multi-degree of freedom system, you know that the terms mass, the damping term, the Fs, in case of the Fs, the K, the stiffness term, these are basically matrices. Okay, so in the stiffness term in the equation, this K term, these are basically matrices. So these stiffness term is modified to recognize the inelastic behavior of a building. So this equation, if you remember, we have written the same for the elastic multi-graffitium system. We have to write the same, but the only difference is that the stiffness matrix K is modified, okay, to recognize the inelastic behavior of a building. Now, in the inelastic case, the force deformation behavior, which is this one. So this is for a structure member undergoing cyclic deformation, is now nonlinear and hysteretic. So you can see the behavior is nonlinear. When we say nonlinear, the fact is that this line is linear, but this is not, let's say, in the same slope of this, so it becomes nonlinear, and it is hysteretic. So one thing we say is elastic. If it goes back and forth on the same path, it is elastic. But if it is having some residual deformation after unloading, so it means it is hysteretic. It is not elastic. Also, this is the idealized behavior. If you look at the structural behavior, the force displacement. So if this is, let's say, the base shear, and this is the roof displacement. So this behavior goes, let's say, linearly for a structure, and after some time it deviates and gets a curved position like this, and after that it reaches some peak value and then drops at some point and so on, because the element inelasticity or this plasticity of the element, it reflects in the force displacement capacity curve of the structure. And you can see that there is a gradual change in the stiffness. It reaches the peak, and then there is a gradual reduction in the lateral resistance or the base shear. Okay, so based on the experimental data, the force deformation relations appropriate for various structural elements like beams, columns, walls, braces, and various structural materials, for example, steel, reinforced concrete, masonry, wood, etc. It have been developed by many researchers. So you can obtain this type of force deformation behavior for a number of structure systems and materials. So using these behavior, obviously with certain simplification to idealize them for simplicity, you can model them in the computer programs for the analysis of structure. Now, as we mentioned that the terms here, they are in the matrix format. So there will be number of equations. For example, there will be, for example, in non-linear equations. Okay, that you have to solve them simultaneously. Okay, so in fact, if you have the mass matrix, let me just write here. If the mass matrix is given, if the damping matrix is known, if we know the force deformation relationship, I will write it with U and the sign of velocity. And if we know what is the input ground acceleration, if we know these, so this is a metric, this is matrix, this is also a matrix because of the K stiffness matrix. And UGT is a vector. These are the time varying acceleration. So once you have these, you can solve this equation numerically. Okay, this is the main equation that you can solve through numerical procedures, and there are a number of procedures available to solve these. And in most of the computer program, these are solved by using those numerical procedures. So I will not go to the numerical procedure, uh, but we will just go and we'll talk about the behavior of such system. Now, what is happening in the nonlinear system in their dynamic response is that the structural stiffness matrix, the K matrix, because mass is constant, damping is constant, but only the K term, the K stiffness matrix is must be reformulated at each instant. So what is done is that it is reformulated, okay, at each time instant. Because the stiffness is no more constant and also depending on the state, loading, unloading, reloading. So what happens is that at every instant of time, the K matrix is reformulated. Okay. So the numerical programs and the computer software, they are capable to do this in few seconds. Uh, and you can imagine they are doing it for hundreds and thousands of structure elements in a real structure. Okay. The problem with their solution is also that the response of the various modes is coupled. So remember that in a real nonlinear dynamic time history analysis, the response is coupled. All modes are coupled. Okay, so you cannot just idealize, let's say, a building with one mode, to analyze it only for that mode, and it will give us a correct answer. But in fact, all the modes, they are coupled. And we will see this in coming slide that in the elastic response, they are mostly uncoupled, and you can divide that problem into a number of problems, like treating every mode separately. But in case of the nonlinear behavior, we will see that you cannot treat them separately. The higher modes depends on the initial modes. Okay, now let's talk about why we cannot use the modal analysis. What's problem with the modal analysis in case of the dynamic structures? So if you remember when we presented the concept of the linearly elastic multigraph freedom system, we also demonstrated through an example that various modes can be combined using the SRSs or the CQSU combination to obtain the story shear as well as the lateral forces, floor forces for the structure design. Also in the response spectrum analysis, various modes can be treated separately. But in the nonlinear analysis, the modal analysis or the response spectrum analysis is not applicable, and we will talk about this and why it's not applicable. So we know that the classical modal analysis procedure is based on the property that the force vector, so in the classical modal analysis, what we do is that we take the effective earthquake force vector represented by P effective N that is varying with the time for the nth mode. Okay. So if you apply this force vector or force at the nth floor, it produces response only for the nth natural mode, for the n natural. And all the other modes, they are not contributing to this mode. Let me just give you an example. Okay, so this is from the past lecture, is the response of a elastic system. This one you see is the response of the system for mode 1, and you can see that the other modes, they are not contributing anything to the displacement when the structure is responding in mode 1. The same is here, the structure is responding in mode 2, and you can see that the other modes, they are not contributing anything. Okay. So let me just go here. Okay. Okay, so what we can observe that for linearly elastic system, this property can be proven analytically that the modes are uncoupled. Okay, so in case of the elastic, okay, in case of the elastic, the modes are uncoupled. Okay, so you can treat each and every mode separately, and then you can combine their final effect on the structure. But we will see that this property is not valid for structures responding beyond their elastic range. We will see from the example figure that the same building, if subjected to ground motion intense enough to cause the significant yielding of the structure, this property is not valid. So let me just mention here that the above is not valid. Let me just say not valid for inelastic system. Okay, let's see here. Okay, so this is the same building subjected to the ground motion, and now in this case, the structure is modeled as an inelastic model rather than elastic model. So what you see here is the response due to the mode 1, and this is when the structure is subjected to the mode 1 forces. So this is what you can see, that the mode 1 is only multiplied with the earthquake forces. So when these forces are applied, you can see that the responses, but the other modes, mode 2, mode 3, and mode 4, they also contributing something. It's a very small contribution, but it is also contributing some deformation. It's not zero. And it basically happens, you know, that when yielding occurs in mode 1, so then the higher modes are also excited. Initially, when there is only elastic behavior of mode 1, the other modes are not contributing. But when yielding happen in the structure, then the other modes start contributing in the deformation. Okay, the same is also for this mode. This is the case when the structure is subject only to mode 2 forces, but after yielding, you can see that the mode 1, mode 3, and mode 4 also start contributing. So this tells us that in case of the inelastic behavior, the higher modes depends on the behavior of the structure. If the structure is behaving inelastically, if it is yielded, so then they will start contributing. Okay. Just one thing, if you look at those figures, let me just see here. Now, in this figure, what you see is the roof displacement here for mode 1 for the structure. And in the second, third, and fourth mode, you see also deformation contribution to the roof. But it's 4.428 in case of mode 2, 2.393 in case of mode 3, and 1.151 in case of mode 4. If you look at the percentage, how much it is contributing to the total deformation, it's 6% for mode 2, 3% for mode 3, and 2% for mode 4. So you can see that the contribution is very small, 2%, 3%, and 6%. So there is a coupling in the modes, but the coupling is, you can say, is weak. Okay. And why I'm saying that it is weak, actually it has some advantage for the practical application of other procedure applicable to the elastic system. And we will see that. So this weak coupling of modes permits the development of the, let me just mention here. So as I mentioned that the modes are coupled for the inelastic system. They are not anymore uncoupled, but the point is that the coupling is weak. Okay? The coupling is weak. If the coupling is weak, the good news is that just like the elastic case, we can treat each and every mode separately. Okay? And we can do the nonlinear analysis of system. And this is what permitted the development of a procedure called as the modal pushover analysis. There is a procedure that is called as modal pushover analysis. Modal pushover analysis, the MPA procedure. And MPA procedure is, we will talk about this a little bit. There is a procedure that is used for the, you can say like static analysis of structure to predict the dynamic response of the structure in a simple way. Okay, so let me just give you a little brief of the modal pushover analysis. Okay, the MPA procedure first. Let's go here. Modal pushover analysis procedure. Okay, here. Okay. So what is done in the modal pushover analysis procedure? The seismic demand due to individual term in the modal pushover expansion of the earthquake force is determined by a pushover analysis. So the, it's better I'll go there. So it's It is not including any dynamic analysis, but it's only including a pushover analysis. Pushover analysis. It's just like the lateral load analysis that we have done also in the model analysis of the elastic system. But we call them pushover analysis because if I take this structure here, okay, let's say it's a multi-degree of freedom system. What is done is that these earthquake forces for a given mode, they are applied on the structure laterally, and they are applied incrementally. Okay, they are applied incrementally uh, in up to a point where a target displacement reaches at the reference point. Let's say if I'm taking this node, this top node of the structure as the reference node, let's call this as a reference node. So I'm applying the lateral forces and looking at the displacement of the reference node. And when this displacement reaches the target displacement, okay, the analysis stops there. And what is done in this procedure is that the base shear is noted at every instant as well as the displacement. So if you plot the behavior of the base shear on Y and displacement of the roof, delta roof, you can say, the top of the structure, this behavior is plotted like this, okay, up to the maximum target displacement. So this is a way what is called as the pushover analysis. So this procedure in the MPA procedure, what is done is that pushover analysis is carried out for a number of modes. For the first 2 and 3, up to 3 is carried out, and it can give you quite accurate analysis. So the first thing is that the model analysis is carried out to compute the eigen values and the eigen vectors. So it gives you the vibration period of every mode, as well as it gives you uh, the model phi values. So it gives you the phi values as well as it gives you the omega n values for various modes. So once you know the phi value and the omega n, let me just go here. The formulation is such that okay, so the lateral forces, they are represented by this Sn star that is equal to mass times the uh, phi vector for a given mode. So phi is basically, these are the deformation values of various of these floors, and every deformation value is multiplied with the mass to give you this force. So these forces, they are Sn star, and every force is equal to mass, floor mass times the phi value or the eigenvalue at that point, the eigenvector, in fact. Okay. Okay. So once these pushover curves are obtained, which is also called as the capacity curve for various modes, then let me just go back to the other slide. Okay, so the same is explained here. Let's say this is an example building of a 9-story. And you can see that there are 3 modes which are shown for this 9-story building. And also for the 3 modes, the vibration periods are shown. T1 is 2.27, T2 is 0.85, and T3 is 0.49. Okay, and we already talked about the number of modes. In mode 1, you can see that the masses are all moving in one direction. In mode 2, some masses are moving in the right direction, some will move in the left direction, and you will see that we will see only one crossing for the deflected shape. And if there are two crossing for the deflected shape, it's the mode 3. So these are the modal forces obtained for the floor using this equation, the M and phi n. So when these forces are obtained, they are applied on the structure, and the structure is pushed to lateral displacement. And when the structure is pushed to the lateral displacement, the force, the resistance, the base shear is obtained, as well as the displacement at the reference point, which is normally the top displacement of the structure or the roof displacement of the structure. So for every mode, you can develop this capacity curve, okay, that you can see. For the three modes, they are developed. So mode 1 is here, this is mode 2, and this is mode 3, okay? And let me just mention here. And on this capacity curve, you see a number of these points. That is written as 0.25, 0.5, 0.75, 1, 1.52, and then 3. These are basically the force demand and displacement demand on this capacity curve obtained for the El Centro earthquake. Okay, and it's not the procedure is not shown here how these displacements are obtained, but I think we already talked about the uh, yes. So I think in the previous lecture we also talked about the inelastic design spectrum. So let's say if this is the spectrum of an earthquake. So for a target ductility, what is done is that the spectrum is reduced. This is the elastic one. This is the inelastic one. Okay. So let's say this is elastic. So ductility is 1 or less than 1. And this is for the ductility, some particular value, let's say 2, 3, or 4. So when this is obtained, you go to the elastic vibration period, T1. You read what is the demand in terms of the AY divided by G, okay? And you know that AY by G, when it is multiplied with the weight, it gives you the yield force. So the Vy is AY by G into W. So you can obtain that. And also, if you remember the equations that we last time mentioned between the ductility and the response modification factor used given by the Newmark and Hahn procedure. So you can use that in order to reduce the spectrum. And so from there you can obtain Vy. You can also obtain the displacement demand because this is a force, but also there is a corresponding displacement as well that you can obtain using the Ay divided by G or the Ay into 1 over omega n square. So using the pseudo relation, you can obtain the displacement demand on the structure as well. So anyway, for a number of earthquakes, you can obtain these points directly on this capacity curve for a given mode. So you don't need to carry out the nonlinear response history analysis. You just need to compute the pushover curve, and then using this inelastic procedure, the constant ductility spectrum or the graphical method to obtain what is the force and displacement demand on the structure in a particular mode. So you do that in a number of modes, and then you combine the answer of these three using the SRSS combination or the CQC if the modes are quite close. So this procedure was tested for a 9-story building in predicting the floor displacement of the structure as well as in comparing the story drift ratio. Okay, and if you look here, so it is showing you the nonlinear response history analysis, which is the actual dynamic analysis of the inelastic system, and then the MPA method, the model pushover analysis procedure that involved the static pushover analysis, and then the computation of the base shear and the displacement for a single mode, for two modes, for combining three modes. So what you see here, these deflected shape, and you can see that increasing the number of modes increases the accuracy of the structure. But what you see in this shaded area is basically the error in the MPA-based prediction, pushover analysis-based prediction, and the in the nonlinear time-based analysis. So in some cases, the MPA procedure is under-predicting, and in some cases, it is over-predicting, okay? This is the displacement, and the same you can see also in case of the story drift. So in some cases, it is underestimating, and in some cases, it is overestimating, and so on. So anyway, but you will see that the error is not at much, and sometimes for the practical application, it's applicable. You can compare these error this way as well. So this is the error in the floor displacement. You can see that they are less than the order of 10 when you include all the three modes. Okay. In this case, in the story drift, it's a bit higher, up to 20%. But again, it's not that serious. But in case of the plastic rotation, hinge rotation, the error is quite larger, like 80% in some cases, or more than 40% in some cases. So anyway, these were the initial work related to the MPA procedure. Later on, a number of researchers carried out work on improving MPA procedure for the analysis of other complex system. Obtained is also the results for the damage pattern. So you can see that this is the damage distribution based on mode 1. This is combining the two modes, and this is combining all the three modes. And if we compare them, I think it's not that bad. The MPA procedure are predicting a large number of plastic hinges, which are basically observed in case of the linear response analysis. So the prediction of the number of plastic hinges is quite reasonable. Okay, so this is the way how the MPA procedure is used to predict the response of the structure using the static procedure. And there are many other procedures also used in practice for the assessment of the structures. Now, related to the strength demands for the SDF system as well as the MDF system. So if you remember, when we are designing structure, so we use this equation, if you remember, for the base shear. If we are computing the yield strength, so we base it on the AY divided by G into W, okay? And the AY can be obtained from the inelastic spectrum. Now, W in this case is the total weight of the single degree of freedom system, or the total weight of building. Okay, and the AY by G, this is the pseudo spectral acceleration. So if you know, for a known ductility, we can obtain this value. If you remember, we already talked about this. If this is the code spectrum, so we obtain the inelastic spectrum using the constant ductility. spectrum. Let's say if this is for ductility 3 or 4, you want to calculate. So for that, knowing the elastic vibration period of your system, you can obtain what is the AY by G. So this is the way how we obtain value for a single degree of freedom system. Okay. But if we take this value and use it for the analysis of a multi-degree of freedom, for the design and assessment of for design and analysis of multi-degree of freedom system. So what is the accuracy? Okay. Now the point is, if you design a single degree of freedom system based on this concept, that let's say I'm designing for ductility 3, this is AYG obtained from the spectrum. Let's design the structure for this because this is the minimum required. Let me just mention here, this is the minimum required strength of the east-wave system to limit ductility to that 3. And so if I design a single degree of freedom system, it will work perfectly. But what about the multi-degree of freedom system? If I design to the same concept, what happens? Let's have a look. Now this is the plot that you see here. On the y-axis, you see the number of floors, and on the x-axis, you see the ductility demand in a given story. So this is a multi-degree of freedom system that was designed for ductility 8. So you can see there's a straight line for the ductility 8. And using the concept that the system is a single degree of freedom system. Okay, because in most cases, this is what we do. But if you look at the behavior, in most of the cases, ductility is less, but there are cases where the ductility is quite larger. For example, you design for 8, but you can get 10. In some cases, you can even get 17 and 18. Okay. And what else is important is that the ductility in height wise in the structure is varying. It's not constant, but it is it's complex and it's varying. So ductility variation it varies height wise, and it also depends on the mechanism of the structure. For example, this is a column hinging mechanism, and that's the beam hinging mechanism. So if a structure is a beam hinging mechanism, you can see that the ductility is quite different than the column hinging. In case of the column hinging, the ductility in the lower story can be very, very high as compared to the single degree of freedom system or compared to the beam hinging case. And there has been a work, let me just mention here, this is the same work, but now it is shown now it is showing only the ductility demand on the first story. So this is the first story, you can see this is the second story. So for the first story here, first story, ductility demand was obtained for a number of cases. For a number of cases of buildings with the story of 2, 5, 10, 20, 30, and 40. So there are 6 cases of buildings, and you can see that their vibration period, they are changing from about 0.25, 0.2, 0.25 to 0.5, 1.5, and up to 2 plus. Okay, and if you compare the ductility, so these are the structure which were designed for ductility 2 and ductility 8. So this is the 8 line, which is a straight shown. Okay, this is the ductility 2 that is shown in a straight line here. But when you compute the actual ductility demand on the structure designed to ductility 2, so you can see that they respond fairly well, okay, across the vibration period. But in a long period like 2 and more, the ductility demand is relatively more than ductility 2. But also, if you can see that right from the very small vibration period, the ductility demand is higher in case of the column hinging structure. So from this, we can see that the column hinging structures, they are relatively subjected to larger ductility in comparison to the beam hinging structure. Can you hear me properly, or is it disturbing you? Can you hear me properly?
Yes, sir. ठीक है लेकिन थोड़ी सी disturbance आ रही है पीछे से.
I'm sorry, वो साथ में कुछ काम चल रहा है नाइबर में.
बाकी सर सही है,
Okay,
100%.
ठीक है, no problem. So if we look at the case for a structure when that is designed for ductility 8, so we can see that the effect is now much profound, and for the particularly for the structure with the larger vibration period in these cases, and also depending on the mechanism of the structure, whether it's a beam hinging or a column hinging, the ductility demand can be very higher than ductility 8. And these are important in case of the assessment and design, because in most of the design cases we ensure beam hinging mechanism, but in case of the existing structure we can also experience a column hinging mechanism. So for that we can see that the ductility demand is way higher. So what was carried out in this regard in the same research is that the base year was obtained for the multi-degree freedom system as well as the one obtained for the single degree freedom system. And this is the what is showing you the ratio of the base year strength required for the multi-degree freedom system to the base year obtained through the single degree freedom design. So when you take this ratio, it ranges from 1 up to, let's say, even in this case, up to 2. Okay, so this is a modification factor that is needed to be applied to the base year equation that provides the estimate of the base year for a single degree of freedom system, but that is used in the design of multi-degree of freedom system. So this modification has to be applied in order to limit ductility demand on the structure. So without this modification, the multi-degree of freedom system designed for that base year will not work. So this was related to the strength demand for the single degree of freedom and the multi-degree of freedom system. Now let's see what happened to the inelastic deformation. So the influence of inelastic behavior on story drift. Okay, because drift is an important parameter that is suggested by the codes for the design, as well as this parameter can be used to, that can be easily related to the damage in the structure as well. So again, let's look at the story drift demand for the same structures. Okay, this is the story drift demand in case of the 9-story building that is designed, there is, let's say, elastic initially, then it is designed for various level of ductility, 1, 1.5, 2, 4, and 6. And you can see that as the ductility increases, let's say from 1 up to 6, you can see that the story drift demand reduces on the top stories. Okay. The reason is that when the structure is elastic, so all the energy is distributed along uh, the height of the structure. So every floor you can see is contributing to the is contributing and is almost equally subjected to the seismic excitation. But what happened is that when healing happened in a given story at a given plastic hinge, so all the energy basically is concentrated at those points, because there is a flexibility that is produced here because the stiffness drops there. So all the deformation are concentrated at those points. So the deformation increases at that point. In the upper stories, then they are subjected to relatively less energy and less deformation demands. Okay, so what we can see that the story drift demand and their height-wise variation of inelastic system, it differ from those of the elastic system and depend significantly on the ductility factor, for which ductility factor you design. Okay. Okay. Now let's look at some other important effect. Let me just mention on this is the P delta effect. When the structure is behaving inelastically, the P delta effects become important. What is the P delta effect? P delta, so this is the P and delta effects. What is the P delta effect? These are basically secondary effects. Secondary effect of the downward forces. You know, when we have a structure here, okay, there is subjected to lateral forces, but at the same time, it is subjected to gravity forces also that is acting downward. So when this structure is pushed laterally, these gravity forces, they change their position, okay? And if you look at these, those gravity forces produces, this is delta because lateral displacement. So with that, vertical loads represented by P, with this delta produces secondary effects on the structure. I mean, this is producing additional demand on the structure in terms of the moments, okay? And you can see that it has nothing to do with the lateral forces. Lateral forces are irrespective of this, they are the same. But this is an additional demand, overturning demand on the structure that is produced. So what are the impacts of this? The impact of this is that if you look at the base shear and the roof displacement response without the period effect, excluding the period effect, and then including the period effect. So you can see that the capacity curve is elastic, then it is having hardening behavior excluding P delta. But if you include P delta, you can see that uh, the elastic, the initial stiffness is slightly affected. The strength remain constant for some time, for some displacement value, but after that it drops and it gradually reaches up to the point when it reaches, you can see almost the zero strength of the structure. And this is the these are the cases where the P delta causes the collapse of the structure. But if you look at this curve that is excluding P delta effect, you can see that the structure is almost safe. There is no problem if you deform the structure to very large inelastic deformation. But in the including the period effect, you can see that if the deformation is quite larger, the structure strength will drop significantly, and this can cause the collapse of the structure due to the secondary effect. So from this, you will see that the P delta effect is very, very important to be considered for the inelastic, for structure responding into the inelastic range. For example, this is the elastic range and this is the inelastic. So in case of the elastic analysis, P delta is not having any important effect. But if it is the inelastic range, you can see that the effect of the P delta is profound on the structure. Okay. So if the buildings are responding into the inelastic range, so it will clearly will give you an idea that the consideration and including the period effect is important. Okay, now let's talk about the influence of the modeling assumption. Oh, sorry, this is also related to the P delta. I'm sorry, I skipped this. This is looking at the P delta effect in the other way, like in the previous, we were looking at the effect of the P delta in terms of the force and displacement, or in terms of the resistance and the displacement. And this is looking at the same effect in terms of the story drift variation along with the time. So what you see here is the behavior of structure including the period effect, and the one excluding the period effect. So if you do not consider the period effect, you can see that the behavior is quite normal. There is a normal oscillation back and forth of the structure even after yielding. This is the point where yielding is taking place. Okay, but if you include the period effect, once yielding occur, the structure the structure does not come back and does not oscillate, but in fact it progressively grow into the same direction. Okay, for example, if you look at the nonlinear behavior, what happened is that when it yield, so it goes into this direction, and this is the cyclic behavior. Okay, so it just progressively grow into one direction, and it grows in one direction, and the deformation is so large that the structure gets instability, the dynamic instability. Okay, because if this is the structure and it is responding laterally, so it reaches to that displacement where the P delta effect is so large that it causes the instability of the structure. But if you are not including, if you are excluding the P delta effect, what happens is that it will not have any problem, and the structure is stable. So it is telling you that excluding P delta effect can give you very wrong results of the numerical analysis. Now coming to the importance of the modeling assumption in case of the inelastic structures. So the earthquake response of a building, we know it can be influenced by the assumption in modeling. For example, how you idealize a structure for computer analysis. So these are the cases of the different structures represented by model M1, model M2, and model M2A. These are based for a 20-story structure. So the structure is a 20-story. Okay. So M1 is basically a model in which the centerline models was prepared, in which beam column were idealized as line elements and were connected at the centerline point, and without considering the effect of the panel. So panel was not modeled in that. Okay, in the second model, model M2, this is the model in which the panel zone were modeled. So the strength, stiffness, and the deformation or the inelasticity of the panel was also modeled in that case. But the third model is the extension of the model 2. That's why it is called as model 2A. But the only difference is that now it's also included the other sources of stiffness and strength, and also includes the effect of the floor slab and so on. So like sometime, this is the simplest model. Okay, this is the simple one. And this is the, you can say, is the more detailed one. So if you do the analysis, what you see there in that model 1, after the first yielding, again, model 1 grows rapidly into that in that direction of the deformation, and the deformation is so high that it causes the instability of the structure. Model 2A is better than model 1, but again, it progressively developed the instability of the structure. But if you look at the model 2A, it developed yielding, but respond back and forth and is not having any problem of the instability. So sometimes using detailed model is beneficial because of course it is giving you the right answer, but it is avoiding the problem that you can have in other simple models. So with this, sometime when we design a structure, we always assume that uh, the beams are rectangular. But when we look at the structure, beams are costed uh, monolithically with the slab. So in that case, if you see for the assessment, it will be very important to consider this as a T-beam rather than just as a rectangular beam. Okay, and there is some interesting work going on with respect to the rectangular beam as well as the T-beam. And using T-beam should give you more accurate answer in comparison to the rectangular beam. If beam and if they are casted both monolithically. Okay, but if you look at the fact, this is the scenario that we always assume in the design as well as in the assessment. So you to also pay attention into these cases which are quite common in our area. Okay, this is looking at the same models, the model 2 and the model 2A, and looking at the story drift demand on a 20-story structure for one of the ground motion record. And again, you can see that the height-wise variation of model 2A is quite different than model 2, particularly in the case of uh, the lower stories. Okay, you can see that model 2 can result in very large story drift in comparison to the model 2A. So this will also give you an idea how much error we can have if we are using very simple model. The model 1 results are not even shown on this plot because uh, it was showing instability and it was not possible to obtain the result for M1 because that shows the instability of the structure. Now, what is done in order to take into account the excitation to excitation variation in the model? So when you are doing the analysis, we know that the story drift, if you look at this plot, is very sensitive to the time variation of the ground acceleration. These are for the 20 ground motion record. So like in one record, you can have a drift demand in here, but in some of the ground motion, you can have a drift demand that is quite larger. Okay. Now it is implying that the response to any one excitation should not be the basis for designing new building. If you just take this record, or if you just take this acceleration record, uh, both are giving you very wrong result. So that's why you should not just do analysis for one record, but you should do it for a set of records. Code like suggest 3, 7, or in some cases 20 ground motion records are used in order to obtain the statistical variation of the drift. Okay, so based on those, you can select either the median value and you can even select the value at other probabilities we just mentioned here. For example, in this case, this is the same structure showing you the median value. So this line is for the median value. This one, this is for the median value produced for the ground motion records having 50% probability in the 50 years. This is for the median value for the ground motion with a probability of 10%. These are the design-based earthquakes. And the third one are for the 2% probability in 50 years. These are basically, in most cases, we call them as the MCE level ground motion. But if you look at the same ground motion, but if you look at the statistical value, this is the median value, these three. These are the median, or the what is called as the 50th percentile. Okay, and these three, these are for the 84th percentile. So if you look at the 84th percentile, it's quite larger than, for example, if you compare this with this, you can see there's a huge difference. Okay, and the difference is because that this is the 50th percentile and this is the 84th percentile. Okay, the 50th percentile means that 50% of ground motion causing demand less than this and 50% causing more than that. And the 84th percentile means that 84% acceleration or ground motion produces demand less than that, but only 16% causes ground motion more or demand more than that. So even still, the 84% is again such a demand where there are 16% of cases where the demand is even higher than this. So sometimes the probabilistic estimate becomes important to understand what will happen. For example, it depends on how much risk you can accept. If you can accept 50% risk, so this is your answer. If you want to reduce your risk and you want to just retain only a 16% risk, so then this is your answer. But anyway, this is giving you a clear information that considering the statistical analysis is very important to understand the variation of the demand on the structure. Again, let's talk about the story drift demand. So again, this is the plot for a 9-story and then for a 20-story structure that was subjected to 3 ground motion record. The Los Angeles, Seattle, and the Boston records. And these record has the same probability, let's say the 2% probability in 50 years, but the locations are different. Okay, so when the locations are different, you can see that for the same buildings, it can have a quite different demand on the structure. For example, in one case, this record, which is for the Boston, has having a very less demand on the structure. But if you compare this with the one that of the Los Angeles, so the demand is quite larger. So depending on the location, the same 10% probability in 50 year or 2% probability in 50 years can have a lot impact on the structures. Okay, so today lecture was a bit shorter, and I completed it in one go using mostly the plots and charts rather than going more to the theory. So I hope that this will give you an idea that what is important when you are analyzing or designing inelastic structure. Of course, the response history analysis is the most accurate procedure for the analysis. And in case of the design, so if you design a multi-degree of freedom system or a multi-story building, so you should take into account the higher mode effect. So one of the procedure that was presented here is that the base shear has to be modified for the multi-degree of freedom system. And again, that depends also on the fundamental vibration period of the structure. And also understanding the statistical variations, which are very important for estimating the demands. And also the ground motion or the location where the building is located is also very important for the response assessment of the structure. So again, case by case, region by region, structure by structure, the response is is quite sensitive. So you have to do it always case by case or project by project to do the analysis of the structure. So it was all from my side. If there's any question, you can let me know. Okay, so if there is no any questions, so what we will do is I will pass this lecture notes to you. We will upload that to the Google Classroom, and we'll share with the video recording with you. So far we have taken the 7 lectures. I will just confirm again if we are having to take the 8 lecture or the 7. If we have to take 8 lectures, so we will take the next lecture on this Friday, and then the next week we will have the exam. Okay. Or if 7 is enough, so then we will have preps for the next week, and then we will have exam in the week after that. Okay, because the time allocated for the exam was 14 to 20. So let's see if we can get a chance for a 1 week preparation, so we can also take that into consideration. Okay, I will give you an assignment, but you have to submit that after the midterm. So during your midterm preparation, you can work on that assignment, as well as once you come back, we will see, maybe we can take the quiz before the midterm. If midterm is in the second or third week of the June, then we have to take a quiz in the next class. Okay. So let me just stop the recording here.